picking up right where we left off. Okay, so changes in internal energy. Here we have this function u. U is a function of v and t. Okay, so we're going to start getting used to seeing these types of three-dimensional graphs. These are often referred to as a surface. So in this case, an internal energy surface. And we just finished that discussion of exact and inexact differentials, or state functions versus path functions. And here's two really good examples of that. Okay, so consider some initial state I, okay, given by ui, and which of course would have vi and ti, and then consider some final state uf, which would have vf and tf. Okay, and we know because u is a state function, when we take uf minus ui, this gives us delta u. But we also know, because it's a state function, the following is true. If I integrate it along that path from I to f, I'm still going to get the same result. Okay? So now, but what if we look at the path? Okay? So in this path 1, you can see that work was non-zero and Q is 0. So what does all that mean? Well, if Q is 0, that means it has to be adiabatic. Okay, so remember, Q is 0, adiabatic. Okay? Work is non-zero, that means it's expanding or it's compressing. And if we look at the way this is going on this landscape here, you can see that perhaps the volume is getting bigger, so that would be the adiabatic expansion. Okay? But now what about path 2? In path 2, work is non-zero, and the heat is also non-zero. Okay? So that means this would have to be in some type of diathermic container. Okay? And so path 2 could correspond to, well, it can't be free expansion because the work is non-zero. So this would have to be reversible work, but non-adiabatic reversible work. Okay? And the important point to note about these things is the paths are very different. So in other words, if I try to integrate Q along this path, this is not going to equal delta Q, okay? Because the heat done is very different for both of those two paths. However, we can say that this is true because U is a state function, okay? And so that's our consequence of exact and inexact differential expressions, okay? So we're going to shift here, and we're going to start thinking about how we can express the internal energy in terms of its variables that will give it that exact differential expression. Okay? So here we have the system, and outside of the system, of course, are the surroundings. And here, this also, by saying TV and P contributes to U, that's like the same thing as saying, let's make it different color so we can make this stand out. That's like saying U as a function of T, V, and P. We know that the internal energy is dependent on T, V, and P. Okay? So now we have to start taking advantage of these definitions of state functions, and we want to come up with a total differential expression for U. So we want to come up with an expression for du. And for now, we're going to choose T and V to make this just a little bit easier. But then we will also play with P, the pressure variable, soon. Okay, but let's just choose T and V for now. And so I'm not going to come up with any crazy like x squared times y squared cosine or whatever. We know that U is a state function. So I'm just going to define it with an exact differential expression. And I can do that via the following. I can say now the partial of U with respect to V at constant T dV plus the partial of U with respect to t at constant v dt. Okay, so I've built up my exact differential expression. Okay, exact differential expression. And now the game that we're going to play is inspect the derivatives and see if we can connect those derivatives to a physical observable. Okay, so we have changes in U with respect to volume at constant temperature and changes in U with respect to temperature at constant V. So does this look familiar? Yep. If you said that's CV, then you're correct. Pretty awesome, huh? Okay, that's CV. So I can now rewrite this equation and I can say du equals this derivative at constant t dv plus cv dt. And what's pretty cool about this expression now is because we're holding volume constant, or at least let's suppose that, let's say we were to hold volume constant, then we know that this whole derivative drops out, and then we're just left with du equals cv dt, which we know is true, right? So that's pretty cool. Okay, so now what about this derivative? Okay, what does this mean? Okay, I'll put a question mark next to this one as well. So let's do a unit analysis and find out. Okay, so the partial of u with respect to v, all at constant t. So we know that u has units of joules, and I'm going to use the SI notation of volume. That's cubic meters. Okay, and let's keep going with this. So a joule is a kilogram meter squared per second squared. Kilogram meter squared per second squared. And then there's still that meter cubed from the volume. Okay, the meter unit and the meter units cancel, and we're left with a kilogram meter per second squared. And if you were to carefully inspect what a kilogram per meter second squared is, you would find that's a Pascal. Okay, so that means this derivative is a unit of pressure. It has to be. If it has units of pascals, it has to be some type of unit of pressure. Well, as it turns out, some very smart, famous people, Joule himself, gave this derivative, this unit of pressure, a special name. They called it pi sub t, which equals that partial derivative, and they call this the internal pressure. And we'll see what that means, okay? Internal pressure. Excuse me. Okay? And we're going to see some consequences of what this internal pressure is. Okay? But all the same now, we can actually rewrite our exact differential expression of u. We can replace those derivatives with their corresponding physical observables, which is pretty cool. So I can say now that du is pi t dv plus cv dt. And that's a much nicer equation to look at than all of those nasty derivatives. Okay? We're going to see some other consequences of these derivatives as we move forward in the class. So we're still going to play with these partial relationships. But for now, we can see that just by making an exact differential expression in u and taking advantage of just that mathematical definition, we extract physical observables that are dependent upon the internal energy, such as the constant volume heat capacity. We know that's dependent on internal energy, or really we should say internal energy is dependent on the constant volume heat capacity. And similarly, this internal energy is also dependent on what we call internal pressure. Okay, so what is this internal pressure? So we introduced the Joule experiment, which I will say as the discovery of, oh, that doesn't look like pi t. It looks like a hashtag. So this is the discovery of this pi t parameter. Okay. So what Joule did in this experiment, he had high pressure gas on one side and vacuum on the other side, surrounded by a giant water bath, okay, in which he had a thermometer. Yes, I did say a thermometer, the requisite instrumentation for measuring thermos. Okay, so what Joule did in this experiment was he expanded this gas from high pressure into vacuum and thought, okay, if there's some type of interaction between these particles. So the whole idea of ideal gas law and real gases was kind of still being worked out at this time. Okay. So, but he said if there's some type of interaction between these particles, as they expand away from each other, there should be some type of temperature change as a result in the conversion of potential energy to kinetic energy, fueling the separation of the gases. Okay, but and so he didn't measure any temperature change at all. So there was no delta T in this original experiment. Okay, so in other words, he concluded that there was no heat transfer. So there was no heat transfer from the gas to the water. Because remember, he's measuring the temperature change of the water bath. So he concluded Q has to be equal 0. Well, this is free expansion. It's expansion into vacuum. Okay? So therefore, work has to be equal to 0 as well. So if work is equal to 0 and heat is equal to 0, we remember the first law of thermodynamics that says delta U is work plus heat. So he also concluded delta U must be 0 in this experiment. Okay? And if we go back to that expression we came up with for U, I'll write it up here at the top. So du equals pi t dv plus cv dt. Okay, he said, well, look, if dt is equal to 0, because there's no temperature change, and dv definitely is not equal to 0, so I'm going to write that down. dv is a finite value, right? The gas changed volume. However, because du was all equal to 0, then he concluded pi t must be 0, and later that was refined. Pi t equals 0 for an ideal gas. Okay? So in other words, there is no internal pressure of an ideal gas. And what does that internal pressure mean? Well, that's related to the attractive or repulsive forces that gases have on each other that influence a change in pressure relative to the ideal value, like we talked about with gas laws. Okay? It can also be shown later. We're not going to do this now, but it can be shown. We'll do this later on in a few weeks. Pi t equals, this is really cool, A over Vm squared for a van der Waal gas. So that's really, really neat. So that is that collisional term, right, that gives us the internal pressure dependence of a real gas. Okay? And also, so let's go back to the basics of that definition. Pi t we recognize was the change in U with the change in V at constant t. So I can make a graph out of this relationship. Look, U versus V. All right. And so the slope of this graph will be pi t. So in other words, right, if I expand this, I can say du equals pi t dv. Okay? So now when I get this graph here, right, we can see two regimes will manifest as a result of the volume. Okay? And so it depends on the conditions. We know that when pi t equals 0, so in other words, when the slope is 0, right, this is a slope. So slope equals 0 for a perfect gas, so no attractive or repulsive forces. However, if we're in a regime here where pi t is greater than 0, we kind of have to think about why a positive slope of this would lead to attractions and why a negative slope of this would lead to repulsions. And you have to consider what's happening as a result of the change, okay? So let's play with these repulsions. This idea of if pi t is negative, it's an indication that repulsive forces are dominant. So if we're starting here at this really small volume and we end here at a larger volume across, let's say, this expansion, right? This is expanding, okay? If as a result of expanding, the internal energy decreases, we know in that initial state, repulsions must have been dominating because those repulsions have the effect of raising the internal energy of a gas. And so if we're expanding these gas particles and the internal energy is dropping to a more favorable outcome, then we know from that initial condition repulsive forces must have dominated. Okay? So now similarly, if we're in this initial condition down here, and by expanding the gas, it has the effect of increasing the internal energy, then what that means is those particles, those gas molecules, were happy being next to each other. They had a very low internal energy. But as we separate them out, if their internal energy increases, they're kind of responding and saying, I don't want that. I want to be close to my neighbor, so I have to increase now my potential energy as you're separating me out. Okay? So that ends up being the result of this internal energy. So it depends on a parameter we haven't put in here, which is pressure. Okay? So pressure will dictate where we're at in this regime of repulsions or attractions. Okay? So moving